meet the Global Senior Design Group. My name is John Gulchra.
I'm Jimena Puga.
And I'm Roxana Riani.
We'd like to thank our faculty advisor, Dr. Benjamin Basil, as well as our funder, Mr. Duriel Taylor, who is the founder of the Global Glowing Well Mobile Company.
And Mr. Taylor is here, by the way, and his mother. Let's give him a nice round of applause.
So our main goal is to design a self-powered illuminated bicycle, which is illuminated by electroluminescent paint. This is just a conceptual picture of what we would expect the design to look like. When we came up with the idea, we identified some specific goals, which were to develop a lightweight frame so that it could be portable, self-generation or illumination of that frame. It should be cost-effective so it can be marketed to a wide range of people, as well as safe and suitable for a wide range of weather conditions, especially in Miami where the weather is so unpredictable.
Some of the initial concepts that, the first initial concept that we explored actually was having a clear bicycle frame using either acrylic, polycarbonate, even some clear composites. But we didn't go about this because it would make for a very bulky bike, and the wiring of all the LEDs and electrical components would kind of be visually unappealing. The next thing we explored was using either slits or putting holes through a steel or aluminum frame for LED components as well. But this starts to degrade the structural stability of the bicycle, and some of our designs even had a factor of safety significantly below 1, so we decided that this wasn't really the route to go. The main forms of illumination that we explored to see the possibilities of how were we going to illuminate this bike were electroluminescence and LEDs. Even though LEDs are brighter, there's a lot more safety risk to consider in the fact that there's thermal management that needs to be considered because they do generate a lot of heat. Electroluminescence, on the other hand, do not generate heat. In fact, electroluminescence is one of the very few instances where a direct conversion of electrical energy to visible light generates absolutely no heat. There's no catastrophic failure, unlike LEDs as well. And it continues to operate even when it's punctured, which we kind of did a little bit, and I'll show you a little bit later. And that's something that you want in an application on a bicycle where you tends to fall on the ground, or you lay it upon something, it gets inevitably scratched. So this is a brief outline of our prototype design and how it all came together. And the first thing we're going to start out with is the LUMILOR electroluminescent paint. LUMILOR electroluminescent paint works just like any other EL display in the fact that it's a sandwich of conductors, dielectrics, insulators, and a phosphor. So the phosphor is that yellow thing that you see in the middle, and that's a solid material that emits light when electric current is applied, which is the electro part of electroluminescence. So it can be applied as a very thin layer, as it is with paint, which is about 3 mils in thickness. And the estimated current from Darkside Scientific, which is the manufacturer that we used, was 0.7 milliamps per square inch. Now the life of the paint doesn't depend on how many times you turn it on or off. It just depends on how long it actually is on or off. It also depends on the frequency and voltage applied, as well as the color. So as you can see here, the brightness, also the luminance, is very dependent on the actual color used. There is no direct correlation between color chosen and life. As you can see with white, even though it's only 40 candelas per square meter, it has a life of about 1,500 compared to blue-green, which has 76 candelas, but it's actually 1,300. So there is no direct correlation. Each has its own individual life, but it's the amount of time that you actually have it turned on. So this is our proposed design. What we basically wanted is a bike that looks as much like a regular bike in the daytime when you don't have it turned on as possible, which is why we wanted it to look like a regular blank bike. Now at nighttime, when you wanted to light it up, that's when we wanted to see the bike. Initially, we wanted the whole frame to be painted, but in order to reduce the cost that it would take, and as well as the current draw, we decided to just go with a slim outline that still defines the shape that makes it evident that it's a bike when you see it, as well as it has some sort of cool Tron inspiration behind it. And we also painted the seat stays that are going to act as the brake lights and turn signals. So this is our actual prototype. Almost looks exactly like our proposed design, except for the seat stays. And that's because if we put the white top coat on it, it would have dramatically decreased the brightness, unfortunately. But as you can see with the regular frame, it still looks white even when it's not turned on. So the next thing that Roxana and John are going to go into is the energy generation.
So energy generation is an integral component in our prototype design. So the whole point, ideally, is to have a self-generating lighting system on this bicycle frame. So So in order to accomplish this design goal, we've decided to integrate a hub generator in the front wheel of the bicycle. So this is a Shimano hub generator. It's not the model we use, but you can see as I spin the wheel, spin the generator, it captures that mechanical energy and produces an alternating current used to light this small LED. So we wanted to apply that to our electroluminescent paint on the frame. So we decided to use a Sun Deluxe Dynahub. This is the model we use, and you can also see it on the front wheel of our bicycle. And the design choice in choosing this specific model is that it's rated for 6 volts and 3 watts, which is pretty much the industry standard in hub generators currently right now. But it's significantly lighter than many of the other models out there, with a mass of 390 grams.
So when we began looking at the hub generator, what was clear was that the hub generator voltage output was highly dependent on the speed that the wheel was rotating. So we decided to test the hub generator several RPMs and correlate that data. What we got was actually quite interesting and a useful predictor of our results, where we got a ratio of about 1 to 10 between the voltage that was output by the hub generator and the RPM, which means, for example, if you need 10 volts to be output, you need the wheel spinning at about 100 RPM. This is actually quite acceptable because for a manageable rider speed of about 5 miles per hour, you can achieve that amount of energy.
So this is the mainframe lighting circuit that we use to power the frame on the bicycle. And this circuit powers this frame in 2 different ways. You can power it directly from the hub generator here, or we integrated an alternate method of powering it from 2 9-volt batteries. So I'm going to walk you through each component, what it does in our prototype circuit. So component number 1 is the hub generator. It produces an alternating current, and that's fed into this purge rectifier, which converts that AC to DC. Then that goes into component number 3, which is a 1,000 microfarad or 1 millifarad capacitor. This capacitor isn't necessarily used to store charge, but it levels out those voltage peaks so that you don't get any flickering in the bicycle frame. And then that's fed into these 2 inverter boxes that were supplied to us by Darkside Scientific. And they're wired in parallel. And what they do is they convert that DC current back to AC and step up. They have a 1 to 10 voltage step up because the EL paint requires a higher voltage. So if a cyclist, say the cyclist stops, the wheel isn't spinning, they can go ahead and activate these 9-volt batteries with this switch, which is a single pole, single throw switch located on the stem of the bicycle near the handlebars. So it's easily accessible for the cyclist to activate. And so this circuit will keep the frame lit when the wheel stops spinning just by these 2 9-volt batteries. So this is just a simplified pictorial flow chart of this same circuit showing images of each component. So here you have the hub generator. This is a PCB that we made with a bridge rectifier. That's this black component here and the capacitors. And this is an image of the internal circuitry of the inverter box, one of the inverter boxes. And of course, this is the electroluminescent frame. And then here you have the switch. And when that's activated, it turns on these 9-volt batteries. We show the 2 different brands that we use during our prototype development. So this circuit's great because it reliably lights the frame. It's compact in design. Everything needs to fit under the seat in the bicycle. And it allows the cyclist to keep the frame lit when the wheel stops spinning. Also, another benefit of this circuit is that at lower RPMs, the frame is going to be dim. So the cyclist can turn on the batteries and supplement that voltage input into the EL paint with these rechargeable batteries here. So because the EL paint is voltage dependent, and the voltage output of the hub generator is dependent on the cyclist's speed. So the slower that you're going, the dimmer your paint's going to get. So here we have a proof of concept where you see the hub generator spinning in the background and lighting the frame of our bicycle prototype. We left the lab a little bit lit up so you can get an idea of how quickly that wheel's spinning in the background.
This is just using the alternative circuit with the bike being powered solely by batteries. You see, even in the night, it looks really good, even though the cyclist is riding at a low speed. So what was necessary at this point was to observe the performance of the batteries, how they would behave when being lit. So we connected the two 9-volt batteries to the frame and allowed them to discharge over time, checking the charge at several points. What we got was that the discharge would occur around 5.081 hours, whereas in theory, using the battery capacity, as they had a capacity rating of about 250 milliamp hours, using the capacity equation where C is equal to current multiplied by time, we got a predicted discharge of about 6 hours, which was pretty close to what was expected, as we got an average error of about 15%. Jimena will now take you through the brake lights and turning signals.
So we incorporated brake lights and turn signals again because this is about safety and visibility, and this was used on the seat stays of the bike. Just like anybody else who knows driving in Miami, how important turn signals are, even though a lot of people don't use them. We incorporated the switches directly onto the handlebars for ergonomic reasons. It's easy to access. If you want to turn left, you use the switch on the left, vice versa. Our brake light, like I said, we use a normally closed switch that's on the brake lever, and on the next slide I will show you how it works in that aspect. We use normally closed with this circuit because when the lever isn't engaged, like right now, the light is off. The moment that I engage the lever, it releases. Is it turning on? No. Did you connect it?
No, yours are connected. But as you talk, I can show.
Okay. So when you engage the lever, it releases the switch, which actually closes the switch because it's normally closed, as you can see. So this happens automatically. The moment you brake, you don't have to worry about turning a switch. It does it for you. Can everyone see? Okay. So this is for our brake switch, and this is again how it works. Just an assembly. We mounted it directly onto the brake lever again, so it's automatic. And we used a nut so that if for whatever reason the switch blew out or it failed, it's easy to disassemble and put it right back on a new one. So the 555 timer, as you can see, this is what it looks like in a little inverter box. We use one in astable mode. 555 timers are integrated circuits that are used for flashing, pulse generators, any sort of oscillating applications. For us, it's basically just to flash the light. So it sends out, as you see here in the output, it sends out a square wave to just turn it on, off, as you can see. This is just a little animation of what essentially works. So first it charges through the two resistors and then through the capacitor, and it discharges just through one resistor and the capacitor. So the frequency is dependent on the value of both of these resistors as well as the capacitor. The high time, which is the time that it turns on, that time that it charges, is dependent on the value of both of those resistors and the capacitor. And the low time, so the time that it's flashed off, is dependent on just that one resistor that it discharges from. So based on our resistor values, and we simulated here, we got a frequency of about 677 millihertz, and which is very similar to what we were able to calculate. And those are the times that we got, 0.977 seconds and 0.488 seconds. So realistically, what you would want, again, to increase the life of your paint is that you would kind of want this inverted. You don't want it on for as long. You will still be able to see it flash, even if you have it on for 0.488 seconds. But it won't be on for as long, so you'll be able to preserve some of the life if you can reduce that and basically just switch those values over. So this is just, I can show you how it works. Here's the rocker switch for the turn signal. So when I engage this one, as you can see, flashes on. It's all integrated easily, so when you're riding the bike, it's very easy to access. Basically what I have 3 switches and 2 light sources. So this creates a little bit of a concern in the sense that I'm getting actually some current backflow. So as you can, this is just a sample, and this is more with, I used it with LEDs, but this is a test circuit that I did. So the power source comes out, and it either goes to the rocker switches for the right or the left turn signal, or the brake switch. So the brake switch, if the brake switch is not engaged, and this one is, then it's going to power this 5.5 timer, as well as the same thing happens if I turn this switch on. However, there's less resistance for the brake switch, so if I press the brake even though the rocker switches are turned on, the brake switch is going to override the other switches, so you're going to see the brake before you see the rocker switches.
So if you apply the brake now, that blinking light will go off and stay still?
Yep.
Is that what you're saying?
Precisely.
Yeah.
So this is just a video showing what I mean by current backflow. What you can see is that I have both of the seat stays are flashing. What you can't see is I actually only have one switch on. So this is what was the problem that I was getting the current backflow, because you have a common node of these 2 sources. So this was fixed by placing diodes. However, the diodes do add a little bit more of resistance, so you have to up your voltage a little bit more as well. So this was again a just a brief diagram. The green is where the current would be flowing. This here is our brake switch, so when this is engaged, this is just a diode to make sure it only flows in that one direction, but these are the two seed states, they represent the seed states like. And this is also, when the switch is not engaged, they're not, these are turned on, so these would be flashing, even though they don't seem as bright. So this is what's actually going on inside of the inverter box. Only difference between the previous circuit that I showed you in the inverter box is this transformer over here, because you need a step-up voltage as well as the AC current for the EL paint, so you can't just use the batteries. The next thing I'm going to go over is the retroreflective handlebars. So I'm sure most of you know about how retroreflective works, and we thought this was actually one of the more unique aspects of our design, because there have been previous that there's retroreflective trimming and glow-in-the-dark handlebars, but there's never been seen actually retroreflective handlebars. So the reason why we incorporated this is because it's obviously no power consumption at all, but it has very high added visibility at night. If you can't see the light, or for whatever reason the light isn't turning on, if a car light flashes towards the bike, you're definitely going to see those handlebars, and it's also a very evident representation of that's a bike. So this is what I was mentioning before, that there is reflective trim handlebars and glow in the dark, but never fully reflective as we have them. The last thing we're going to go over is the system integration and assembly. So all the blue dots basically represent key components of how we were able to bring this together into a seamless design. So the first thing we have here is this is the encasement that we designed. So this is going to hold our inverter boxes and our batteries. This is the seat post, and this is where those things are the leads for the EL paint. We actually had a bit of a problem when we received this, because as you can see, it's very high up on that seat post. And as you can see on our actual seat post, there needs to be a seat clamp in order for the seat to go inside. So we actually had to remove those and bring them lower, which was quite a challenge, and thankfully it still lights up and it all works. And we use a mechanical connector, so that way if you need to change that as well, it's easy to remove versus having all that covered in GP welded and soldered on. So the way we also routed the wires, we have about almost 10 wires coming out from the handlebars just for the switches that need to go towards the end of the encasement. We didn't want 10 wires going across the bike, so we drilled 2 holes to the top tubes, and we routed them through the top tube in order to make it, again, as seamless as possible. This is also how we integrated the switches on the handlebars, and we wired all those wires through the actual handlebars and in the stem. As you can see on top, that's the switch for the mainframe, and then it comes out and onto the top tube. So our encasement is designed to hold 6 9-volt batteries and the 4 inverter boxes. There's 2 for the mainframe and 1 for each seat state. They attach to the bottom of the saddle, as you can see, with zip ties for now. That's not the final design. And they're designed with holes on the bottom, as you can see here, so that it's easily connected to the quick connects for the actual leads of the frame. They're also, right now, it's still in the preliminary design to be entirely waterproof. Right now it's mostly water resistant, so if you get caught in the rain, you will be fine, but don't plan on throwing your bike in the pool, because you won't be fine. But that is in our still finishing stages of making this entirely waterproof. So that if you wanted to throw it in the pool, I mean, that's up to you. But so the waterproofing, what is for right now currently waterproof are our switches. That main switch that we have, that's a marine grade switch, and that is definitely something, if you get caught in the rain, it's right out in the open, you don't want that to be shocking you, as well as we weren't able to fit these waterproof switches onto the handlebars because they were too large. So what we did instead is we used the same small rocker switches and we heat shrunk them, and then we have the clear bike grip tape on top of them as well.
So we were trying to investigate different ways of lighting the frame when the wheels stop spinning. So ideally for future designs, we wanted to integrate some battery charging capabilities where the hub generator will charge 2 9-volt rechargeable batteries. So you see here, this is just a simplified flow chart where we have the hub generator and the rectifier, and then we put here rechargeable batteries that can accept charge from the hub generator and simultaneously discharge onto the electroluminescent paint. So initially we started by trying to charge 2 9-volt batteries because the optimum design voltage is 18 volts to keep this bike frame illuminated in an optimum range. So unfortunately, this circuit didn't work because to charge these 2 9-volts, you need to overcome theoretically the 18 voltage potential across them. And this hub generator, on average, can output about 10 volts, maybe 16, it might peak at 16 if you're lucky, if you're going really fast, but that's not under normal ideal circumstances. You also have to keep in mind that across this bridge rectifier, you're gonna have about a 1.5 voltage drop. So that's the reason why our double battery charging circuit was unsuccessful. So we decided let's try with charging one single 9-volt battery, which did work. And you'll see this is our electroluminescent sample. And in the beginning of the video, it's a little bit dim because that battery is about 50% charged. And as the wheel starts spinning, the sample brightens up, indicating that that battery is being charged. So the hub generator is delivering current to the battery and the sample at the same time because they're connected in parallel. Then when the wheel stops, that's okay. When the wheel stops, the sample's brighter than before, indicating that our battery was charged. We tested this battery before and after running this test, and it had gone from a 50% charge to about an 80% charge. So we were able to successfully charge one 9-volt battery, but the problem is that 9 volts is not going to light our frame. We need at least 16, preferably 18. So we try to integrate a DC to DC converter into this single battery charging circuit. So what this DC to DC converter does is it takes an input voltage and it steps it up to whatever you adjust this potentiometer here to. So we wanted an input voltage of 9 volts. We set the potentiometer to 18, and we expected a current draw of 560 milliamps. But something unexpected happened when we actually integrated this converter into our circuit. The input voltage, when we actually connected it, dropped to 3.1 volts. Output voltage dropped to 8.5, and our current draw spiked to 2 amps. So there was some signal interference with this inverter box, with this converter in the inverter boxes that caused this spike. So next we decided let's investigate the current draw of this EL paint on the bicycle and on the sample to see why that DC to DC converter wasn't working. So you see here, the orange plot is the bicycle frame, the current draw for the bicycle frame as a function of input voltage, and the blue plot is for the sample. So we expected, given this 0.7 milliamp per square inch specification, that we would have a 98 milliamp current draw of the bike frame at 18 volts. But you see here that it was almost 6 times what we expected. So the actual current draw at 18 volts for the bike frame was 560 milliamps. So we believe that that contributes to the failure of our DC to DC converter.
Okay, so we're running kind of close on time. I'm just going to go over kind of why this matters a little bit. This is an interactive map of the cyclist fatalities in Great Britain over the course of 30 years. It's a lot. Averages out in America to about 13 per week if you talk about just fatalities, and 49 per week in the European Union. And 57% of the reason why this happened was because the driver essentially didn't see the bicyclist.
What is also significant is that if people feel safe to ride their bike, they might be encouraged to ride their bike some more. And 57% of all gas emissions in the US were actually fossil fuels, and 30% of that is actually due to transportation. So if people ride their bike more often, that can reduce the carbon footprint that we may see. The economic impact that we see also is that one major fact was that in 2013 in the European Union, the cost of health, the health cost due to just road accidents was $160 billion.
That was just for cyclists.
Yeah, that's just for cyclists who got in fatalities. This is the project cost. The project costs about $9,000 overall, as well as the high gas prices that we experience in the US is felt all over the world, with places like Norway paying like $10 per gallon for gas, as well as places like India having an unaffordability of 100%, which means that for someone to purchase gas in India, they need to pay 100% of their daily income. The bicycle we used met the international standards, which means that ethically it would be safe to be used in different countries.
The Global Bike self-powered and sustainable design supports environmentally friendly movements in Western culture and can also keep cyclists safe when riding during heavily trafficked areas in urban cities.
So this is the timeline of our project, our team members, some references, and some people we'd like to thank, especially Mr. Duriel Taylor, Mr. Benjamin Basil, as well as Kevin Longo. Have you any questions?
Any questions? You're looking at me. Both of you looking.
Go ahead, no,
There's really only one question. It's the cost benefit analysis, guys, on spending $9,000 to make a bike.
Well, that's just a prototype cost.
What do you think the cost would be commercially?
It would dramatically decrease because if you manufacture paint yourself, not do it how we did it, the cost is dependent per gram and it's the order, and that cost dramatically decreases the larger your
How
order
dramatic?
is. For example, one of the things would be you need silver, phosphor, the encapsulant. Silver was probably one of the more expensive ones, and if you went from just 100 grams order, you have about 170 rough estimate per gram, I think it was, and if you drop down to the highest that they have the order, you can go down to about 70 cents.
But what are you competing against? You're competing against people that have retro-reflective material on their bike.
Retro-reflective material on the bike isn't the same thing. You need the light source.
A tire on, or a light on the front, a light on the back that they paid $50 for.
True, but the whole point is that we were trying to do something that isn't available on the market. You see a light in the front and a light in the back, and we are actually talking to somebody that it's like you have that bright light, and you're driving and it's actually blinding you. It's not really helping you be more visible as a cyclist. As a driver, you're just trying to not crash into that, whatever that bright light is coming from. It doesn't show that it's necessarily a bike, it's just a bright light. And what we're trying to do is that we're not trying to blind anybody necessarily, we just want to make it obvious, like, I'm a bike, this is what it shapes, this is what it looks like. It's not the same thing as an LED. You can't really compare the two in the sense of what we're trying to accomplish.
Okay.
Just to add to that, I think economies of scale will speak to that as well, once you start producing some volume.
Yes, mass production is
As long as it
significantly
gets it
decreased
down
cost per
to
unit.
somewhere in the $10 range. Yeah, maybe $50 range.
$50 range of what?
As far as the
cost for
lighting system
production.
itself,
Yeah, I mean, that's where you're gonna have to be in order to be commercially. I mean, because people sell things for 50% more than what it costs.
Well, the cycling community actually spends a lot more money on their bicycles than that.
Yeah.
I'm a cyclist myself, and I know plenty of people who spend more than $5 grand on their bike easily.
Yeah.
So if it's something that lights up and it's bright like that, and they don't have to, I love riding my bike at night, especially in Miami where it's hot in the daytime. But I'm scared half the time because I'm gonna get hit, and I have been hit twice. But I still go because I like to ride my bike. And I have one of those bright LEDs that's 2,800 lumens, but I have to point it downwards because if I point it upwards, I'm gonna blind whatever car is in front of me. So if I have something like this, I don't have to worry as much because the car that's in front of me is gonna see my handlebars. I don't have to blind him. And any cars that are next to me are gonna see the shape of my bike, and they're gonna see that I'm a bike.
Yeah, in their defense, people buy Rolls Royce and some people buy Volkswagen.
But the cost of the electroluminescent materials that's the most expensive part, and that's what you're paying for. It's a completely different
Okay,
comparison. for
another
LEDs.
question, why did you select blue?
We thought the sample was blue.
Yeah,
The
the
sample was
sample.
very bright. The sample was actually blue-green.
Because
that
the
was
green
the-
actually had better data.
Of course. That's where our confusion was. That was a mistranslation with the company. But ideally, you want the brightest light that you can get. So ideally, if we were to go back in time, we would definitely do blue-green.
Yeah, the funder, I think he's got some response to your question, Dr.
Well, no, not a response. I was just gonna say that there's a rumor that this bike also is gonna be able to charge cell phones.
yes. Actually, we didn't incorporate that into our senior design, but that is functional. I have a separate video, it's not in our presentation, but yeah, we integrated USB charging capabilities so that when you can light the hub, you can have the hub generator lighting the frame, or you can have it charging a USB device. That's initially why we integrated these batteries. So if you want to charge a USB device, you can charge it and flip on the switch and have a charging bike as well as an illuminated bike. We just didn't include that in that presentation. Yeah. That's part of our final prototype design for our investor.
I'll pay $10, $15 more for that.
Yeah,
For that capability.
And you know, ideally, cyclists would like, if say they're on a longer ride or a race, they would like to keep their phones, GPS charged while they're riding. So that's really what that's for.
Okay, any other question?
Two comments. One, your pros and cons, really good. You guys lined them up. And second thing, you sent a doc, a Word document rather than a PDF. I believe was posted out on the website.
Oh, that's not their fault, that's ours. We
Okay.
should have done the conversion, so take
Okay.
that off them.
All right.
All right. Any other questions? We were pressed for time, so we had to get them out there.
And we're sorry we went over.
Yeah.
Oh, you're fine.
Yeah.
Okay, well, thanks very much.
Right.